concentration in the center, and then there's a big void, and then there's another big ring out here. And so what we found from this is the universe is actually full of surprises. It looks like there's mass where there isn't light, or where there's not a significant amount more light than there is where there isn't very much mass. And so this is a big surprise, and we're stuck trying to figure out why. So let's ask these two questions. Let's ask these two separate questions. First, let's ask, how much light is there? Which means how much mass is there in stars? How much of the universe is in what we know of, what we're used to, stuff like our solar system? And then we'll ask how much mass is out there. Remember, we can figure out mass just from gravity. We don't need to measure the light to do it. So for light, that's pretty easy. This is a picture of the Hubble Ultra Deep Field. What they do is they took the most powerful camera on the Hubble Space Telescope, and they just pointed it at a completely black patch of sky. Something where we said, we know there's nothing here. We've looked with all the telescopes we have, we don't see a thing. So they just point it at this black patch of sky and wait. And they sit there and they wait, and this is what you get. So even something that looks completely empty, completely devoid of matter, is full of stuff. You can see galaxies. Actually, every dot you see in this picture is a galaxy. So the universe is a very big place. We estimate that there's a total of about 100 billion galaxies in the universe. And yet, when we add up each of these dots and say, well, if there's this much here, let's extrapolate how much is over the whole sky, we find that only 0.5% of all the energy in the universe is in stars. And we learn that from looking at light, and we can look at this in any frequency we want. And this is the conclusion we reach. So that's a really small amount. Now, on the other hand, instead of just looking for stars, we can do the same thing with gravity. Most galaxies are concentrated in these giant galactic clusters. So this is an example of a cluster. This is cluster Abell 2218, although you could do this with any galaxy cluster you like. This is a galaxy cluster that has about 1,000 galaxies in it. So it's a medium-sized galaxy cluster, a little bit on the big side. What we see is, well, just like in the solar system or just like in our galaxy, what we do is we measure how quickly these galaxies on the edge of the clusters are moving. When we see how quickly they're moving, if we know they're in a stable orbit, we can figure out how much mass is inside there. So how much mass is in the galaxy cluster to keep this thing down to it. And instead of 0.5%, the number we find is that 20 to 30% of the total energy in the universe is in these galaxy clusters. So what this tells us is either the laws of gravity as we know them are wrong, or most of the matter in the universe is not in stars. So those are the two possibilities. So either we need to change the laws of gravity, or we have dark matter in every galaxy and every galaxy cluster in the universe. So let's see where we get from this. Oh, I'm sorry. I want you to notice something about this image that those of you who are photographers might notice is a little weird. Does anyone notice these little arcs in the image? All right. Does anyone have any idea what these arcs are? You know?
Lensing.
Oh, wow. Yes, they are. Yes, it is. Most people say that this looks like a scratch on your lens. Most people say this looks like one of those sunburst effects. But no, this is actually something called gravitational lensing. And I'll show you a little video of what this does. If I have a mass, and then I have something behind that mass, what I actually see is the mass gets stretched by whatever's in between it and us. And it can make these arcs, it can make rings. And so that's what we see. When we look back at this image, that's gravitational lensing. That's having a big, heavy mass behind something else. And gravitational lensing can also tell us where that mass is. And so what we find, what you might expect is, hey, yeah, mass should be clustered in all of those galaxies. And it is. Each of these spikes is a big galaxy. But there's something extra going on too. You might notice at the center, there's a giant bulge right here. And in addition, there's a bunch of spikes on top of it. But that giant bulge, the only thing we can think of is that's got to be dark matter. There's got to be this big halo of dark matter, not just around the galaxies to make the rotation curves flat, but also around clusters of galaxies. There should be a giant halo in order to keep things gravitationally bound and to make the gravitational lensing work out. So mass is not even necessarily in galaxies or in the stars. It can be bound in clusters as dark matter. I want you to take a look at this. What if we could take two of these clusters and smash them together? What would we see? So someone went and ran these computer simulation and got a neat little shockwave like that. So that's what they get when they simulate two clusters colliding together. So I want you to notice, I'll show it again, I want you to notice the features to what happens in the center. This stuff that you see is representative of all the gas, all the dust, and all the stars that we find in a galaxy. It's all the normal matter that we see there. And I want you to pay close attention to what happens. Okay? So we've got one galaxy cluster coming in, smashing into another one, and you'll see they pass through each other a little bit. Some gas gets expelled, and then they merge together. Okay? Normal matter sticks together. All right. Now this is an example, it's hard to tell just from looking at the optical image, but this is an example of two clusters that had just done this. This is an example of two galaxy clusters, two groups of galaxies that have just smacked into each other. Now it's really impossible to tell just from looking at the visual image. You might be able to see if you've been looking at these for a while, yeah, it looks like there's probably a cluster over here, and it looks like there's maybe another smaller cluster over here. But what we can do is we're not stuck looking at just visible light. We can also look at X-rays. X-rays are produced when you have much hotter gas. So when galaxy clusters smack together, they get heated up, the gas in them gets heated up, and they emit X-rays. So we have the Chandra X-ray telescope up in space, and I'm going to overlay the data from the Chandra X-ray telescope on this in pink. I hope. Maybe if I do it by hand. All right. And so what you see, these shocks look very familiar. These look very similar to our simulations as we see these gas shocks. But we have another tool also. Remember, we know gravitational lensing. So that's going to tell us not only, so X-rays will tell us where the gas is in this collision, but the lensing data is going to tell us where the mass is, where all the matter is. And if we take a look at that in blue, you see that it's way out here and way out here. So what happens, what it looks like has happened anyway, is two clusters came together, the gas smacked together and collided, and it passed through a little bit, but it shocked and slowed down. But this blue stuff, this stuff that we don't know, that we can't see, it just passed right through each other. It hardly slowed down at all. And so what we can conclude from this is that, wow, this stuff over here, whatever this is that has mass, that's causing this gravitational lensing, it is not normal matter. It is not protons, neutrons, and electrons. It is not all the stuff we know in the universe. And the way we know that is if it was that same stuff, it would have stuck together here. We would have seen this lensing data exactly in the place where we see the X-ray data. But we don't see that. And so what they did then is they said, well, what if we took our cluster collision simulation and we ran it specifically for this configuration? So I'm going to put gas in pink and dark matter in blue. And I'm going to run a simulation and see what happens. Right? So they come together, they collide,